Welcome back, everyone. In part 3 of the Keras syntax basics, we're going to focus on the evaluation of our model. Recall that we have this test set that we can compare our model's predictions to evaluate how well our model is actually performing. Let's head back to the notebook and continue where we left off. Okay, here we are where we left off last time. Now, with this plot, I can see my losses on the training set. But what I really want to know is how well will this model perform on data that it's never seen before. And that data is our test data. There's lots of different ways we can evaluate, so we're going to walk through a bunch of different methods. And a lot of these will return back the same result, some mean squared error. So we're just going to go through the various methods of doing this. One way to do this is by calling model.evaluate. And the way model.evaluate works is you pass in your test set, x and y. So what I'm going to say is x test and y test. And I will say verbose is equal to 0, so I don't see a bunch of output. And if I run this, what happens is it returns back your model's loss on the test set and y test. So what this number actually represents is the metric loss that you decided on. And if we take a look back at our model, in our case, that's mean squared error. So what this means is on the test set, that is data it's never seen before, it's getting back a mean squared error of 24.97. So we could do the same thing for our training set. So we could say model.evaluate xtrain versus ytrain. Run that, and we see the loss on our training set. Keep in mind, your values may look slightly different just because of the way the neural network works. It starts off with random initializations, so you may get numbers that are slightly different. However, after training on about 250 epochs, you should be hovering somewhere between 24 and 26 as your mean squared error. So what does this actually mean? Well, this is a way we can interpret our results to see how well the predictions are actually performing. And we'll show you how to also grab root mean squared error and mean absolute error. So the way we can do that is get our actual true predictions. And we do that by saying model.predict, and we're going to pass in our test to get test underscore predictions. So what this does is we pass in our test features and have the model predict, just based off those features, what it thinks the price should be. So now here's a list of the prices that it predicted based off our X test set. And in fact, let's bring these together along with the true values for that test set, that is the Y test, and then we can plot them out and compare them against each other. So what I'll do is the following. I will create a data frame called pred underscore df, so my prediction data frame, and it's going to be equal to, and in this case, I will say that my test predictions are this model.predict, and I will turn those into a pandas series by saying test predictions is equal to pd dot series test underscore predictions, and in this case I will need to reshape this to be 300 comma, and that's just so it matches up with the dimensions that a pandas series call expects. So essentially, after running this, I still have those same test predictions, but it's a pandas series now instead of a numpy array, which will allow me to do the following. I can say my prediction data frame is equal to pd dot data frame based off y test. I'm going to say the columns here are just test true y. So right now my prediction data frame just has the true value of y. And what I'm going to do is say, go ahead and concatenate that with the true value of y, comma, with my test predictions. And I know there's a lot of code here, as well as a lot of braces, brackets, and parentheses. So if you get an error somewhere, go ahead and check out our notebook and just run that directly. And here what I'm going to do is also make sure that I'm joining these along axis equal to 1, so along the columns. After running that, you should be able to see your prediction data frame, which is essentially looking like this. We have test true y, and here we get 0 because we don't actually have a name for that. So I'll go ahead and say my columns are test true y, and then my model predictions. So now when I take a look at my predicted data frame, I get this result. So here I can directly see, based off my test set, what the true price value was and what my model predicted. Okay, so what I can do is lots of things now. I can actually plot these against each other. So what I could do is say, create a scatter plot based off this data in my prediction data frame. And then I'll also do the following. I'll say x is equal to test true y, and I'll plot it against these model predictions. So run that, and we see this result. So what does this actually mean? Well, let's imagine that my predictions were a perfect match for the true y prices. That means I would expect a perfect straight line here, because if my price was 300, then my prediction should also be 300. Now notice, we actually are quite close to a very straight fitting line, which means this model is performing very well. And we can also grab metrics to essentially show that not just qualitatively through a plot, but quantitatively through the various regression methods that we talked about. Recall back in the machine learning lectures, we had a whole discussion on regression evaluation. So we talked about mean absolute error, mean squared error, and then root mean squared error. So let's show you how you can actually grab those. To do that, I can say from sklearn.metrics import mean absolute error and mean squared error. And if I want my mean absolute error, then I just need to, if I take a look at this, compare my y true to my y predicted. And luckily I've already organized that for myself in this data frame, where I have my test true y, and I also have my model predictions. So I run that, and I get a mean absolute error of about 4, which is something you should be getting. You should be getting or somewhere around 4 for a mean absolute error. So this means, on average, I'm about $4 off from my price point. Now, the most common student question I get is, how do I know if this is good or bad? Well, it really depends on your original data. If you take a look at our original data frame, recall we have this price column. Let's go ahead and call .describe on this. And we can see that the average price is around $500, with a minimum of 223 and a maximum of 774. And our mean absolute error, that is how on average, how far off we are on average off by $4. So if I take a look at the mean price, that's less than 1%. So that would mean that this is actually a pretty good mean absolute error, something indicated again by this plot right here that's almost a perfect straight line. So this indicates that our model is performing very well at predicting the price of, let's say, this gemstone based off these two features. Now again, the mean absolute error doesn't mean anything without the context of the label you're trying to predict. If the average price was $1 and our mean absolute error was $4, that means we're off by 400%, and that's a very different story. So you always have to take into account the mean values as well as the actual distribution of your label when comparing it to your error, such as mean absolute error. And we can also calculate our mean squared error by performing the exact same thing. So I can say mean squared error, go ahead and copy and paste this, and notice it's 24.97, which is essentially the same thing we got at the very bottom here when we said model.evaluate on x test versus y test, which makes sense because the original loss for the model was mean squared error. So essentially what this model evaluate line does is exactly what this line does. It just calculates the mean squared error for whatever you pass in, either the test set or the training set. And if we wanted to get the root mean squared error, then all I would need to do is essentially take the square root of this, which is the same as taking something to the power of 0.5. You could also say np.sqrt if you've imported numpy. And then we get back the root mean squared error, which is 4.99. So you can use the mean absolute error, mean squared error, and root mean squared error however you see fit to evaluate your model's performance. And finally, I want to go over two last things, which is predicting on brand new data. So let's imagine that we go out into the field and I pick out this gemstone from the ground, and it has these features. Let's say I pick out this new gemstone and pay attention to my dimensions here. I have double braces so that it matches up with the original data. And feature 1 is equal to 998, and feature 2 is equal to 1,000. And these are just made up features. So I picked this new gem out of the ground, and now I want to ask my model, what should I price this at? Well, the one thing I have to remember is that my model is trained on the scaled features. So what I have to first do is take my original scalar and transform new gem. So now I have the scaled version of these features. So let's go ahead and set new gem equal to the scaled version of new gem. And now what I can do is simply take my model and predict the price of that new gem, which in this case should be somewhere around $420. So that's how you would predict on a brand new set of data. Keep in mind, that's the exact same process you just ran on your test data set. Since your test data set, according to the model, is essentially brand new data it's never seen before. So the way you evaluate your test set is basically the exact same thing you would do for brand new data. And finally, if you're running a very complex model that took a lot of time to train, you want to make sure that you save that model. And Keras makes it quite easy. We simply say from tensorflow.keras.models import load model, and then I take my current existing model and I save it as a HDF5 file. So I can say some string myGemModel.h5, run that, and now what I can do is use the load model command. So later on I can say, okay, I'm in a new notebook and I want to load up this model. I simply run this import command of load model, and I say later model is equal to load model, and then I read in that model I saved, my gem model.h5, and then you may get some warning there based off the input shape. You can totally ignore that warning, it's okay. But notice, now I can treat this later model just as I would any other model, and then predict on new gem just as I did before. And notice we get back the exact same results. So that's how you can both save a model and then load it later in a new file. Okay, so we went over the very basics of Keras. Now we did this on a fake generated data set. Coming up next, let's focus on a much more realistic data set and really focus on the full workflow, including exploratory data analysis and feature engineering, which is very crucial to becoming a good machine learning practitioner. Thanks, and I'll see you at the next lecture.